family, so they do a lot of things the same way. Yes, but we will go into that. Did I not give you guys a homework to work on?
Yes.
What was it? Can we at least do one together? Show of hands if you at least attempted those mechanisms. Those are very important mechanisms, guys. Making acetals, hydrolyzing acetals, those mechanisms come up quite often. Yes, sorry. Can I borrow your book, please? Oh, something.
Yeah.
This is easier. Oh,
I forgot my
That was the
notebook.
first day I went.
no, that's not.
I forgot my notebook. How did I forget my notebook?
Okay, but it doesn't.
Oh, I asked you to tell me how to do the synthesis, not a mechanism.
You did sequence of events. Yeah.
Oh, I see. Okay, I was.
No, but there was also
Oh,
two.
shoot, it's
well,
gone. I think I touched something.
but they're not important.
Yeah, what was it? I borrowed yours.
That's what I got.
Okay, so it was for you to tell the size, is that right? Was the first one where, or did we already do this one?
I think you already did that one. That's the one where the
The example?
yeah.
Okay.
Yeah, that was an example.
So
They
the
were-
next one was. Oh, I see. So I wanted you to tell me how you would, and I'm not asking mechanism here, I'm asking for reactions to convert the given reactant into the product. Okay. Anybody? Some of you said you did it.
Yeah.
How? Step one?
Make acid.
Okay. Make an acetal to protect what? And what are you using to make an acetal?
I did.
Like a diol with two.
Right. So remember, we want to try and make a 5-membered ring or a 6-membered ring. That's carbon 1. So we need 4 more atoms or 5 more atoms. 2 of those are, of course, oxygens. So you can either use this diol, or that will give you a 5-membered ring, or you can use this diol, which will give you a 6-membered ring. So that's either of those is okay, but it has to be in presence of
An acid.
An acid.
exactly. Okay, then what did, so we protected this. Then what?
Grignard.
Grignard, what? How much?
2 ETs. I'm sorry, I'm just reading the way I wrote it. 2
That's
ethyls.
okay. I'm sorry, could you say that one more time?
Excess of ethyl and GPR.
Why? Why excess?
Because you have to do it twice.
Exactly.
Yep.
Esters. Remember that esters and acid halide react with 2 equivalents minimum of Grignard. So you at least have to have 2 or excess. Otherwise, it's not a good weight. It won't work. So does everybody remember that?
Yes.
Everybody? Okay. And then what? So
Um,
that will that will convert this into the acetal still remains intact, because acetal does not react under basic or acidic conditions, but this creates the mechanism you should know. It's the mechanism you should know for this, you should know the mechanism for this, and then what?
the oxygen gets protonated.
No, so
Like-
what are you using?
Oh, dilute acid.
Because again, the mechanism you should know. We're not writing mechanism, no, just writing synthesis. Does everybody, is that what everybody got? Yeah, Jason.
When you're writing like the dilute acid, so you need it for the oxygen, the negative charge, and to reverse the.
Everything.
Do you need to put excess?
Of what? That's a good question. Excess of what?
Excess of dilute acid.
What does dilute acid mean?
Water.
What's the role of the H plus in that step? Again, you gotta think of the mechanism.
Protonate.
Protonating, but then eventually what? If you think of the mechanism of the acid, what is it reacting as?
Catalyst.
It is a catalyst.
Mm-hmm.
So if it's a catalyst, it's being used and produced. Used and produced. Used and produced. You need an excess.
No.
Catalyst, you never need more, because again, that's the thing, right? It recycles Now, here's the practical aspect of it. Whose excess do we really need? Water. But if you're going to have dilute acid, is it water already in excess? Does that make sense?
Yeah.
So practically speaking, I mean, it's already excessive water. It's lots of water because you said dilute. Make sense, everyone? Is this what everybody kind of sort of got? And was it just one? Okay.
Yeah, there were just mechanisms, but
Okay.
normal.
Normal.
Like,
Okay, I don't remember the number. Reaction number is, can someone tell me what the reaction number we were at the last one?
That was reaction number 3.
3, okay, so let's get to 4 then. Reaction of aldehydes and ketones is what we are discussing right now. So reaction number 4, which is actually very, very similar to acetals and all, because these are making thioacetals. Thio refers to sulfur, by the way. Thiols are alcohols with sulfur instead of oxygen. Thioketones are ketones, but instead of oxygen you have sulfur, so on and so forth. Thioesters and blah blah blah. Thio is indicating sulfur instead of oxygen. That's what it means. Okay, so this one we've seen before. We're just looking at it again. If you have an aldehyde or a ketone and we react it with, just like instead of a diol, if I reacted with a dithiol in presence of a catalyst, acid catalyst, what would that create? Anybody?
A thioacetal.
Thioacetal. In this case, it
Thioacetal.
would be a cyclic one, right?
Yep.
And what size ring would it be? So again, carbon 1, 2, 3, 4, 5, 6.
6
right?
membered
6
ring.
membered ring. Everybody agrees? Everybody okay? Now, we saw this before, and that was specifically for aldehydes. We saw this, right? Where you can use butyl lithium that gets deprotonated, becomes a nucleophile, you can do SN2 and then convert aldehyde into a ketone. We've already seen that reaction. Just FYI, the thioacetals can be converted back into the parent ketone or aldehyde also with dilute acid, just like acetals. But there is one other reaction that thioacetals help us do. One that we've already seen before, I'll just write it here. Once you get that butyl lithium and then R prime X do an SN2 reaction, and then H3O plus converts an aldehyde into a ketone. We already saw that, right? We've already seen that reaction. But there's one other thing they can do, which is if you treat it with something called nickel. It's basically nickel metal with certain groups on it to control the reactivity of nickel itself as a catalyst. It basically converts the aldehyde or ketone, whatever that is, into an alkane. So the C double bond O becomes, please notice from the beginning, the C double bond O becomes CH2.
I'm sorry, what was runny?
Nickel is something called, basically it's nickel with certain groups which we are not getting into to control the reactivity of the nickel. That serves as a catalyst. It's called nickel.
It's a can.
Okay, so again, in terms of mechanism, we should just be able to write this mechanism and this mechanism. Those mechanisms we don't need to know. And these mechanisms are exactly like the mechanisms for acetal. Making an acetal or hydrolyzing an acetal, exactly the same mechanism. Does that sound okay? Yes? Okay. Let's just look at a couple of examples to get an idea. So for example, That's a U, sorry. Please feel free to go write the answers out quickly.
Carboxylic acid.
Hmm? Oh.
Next one. Are you going to the making it clear up?
What, actually? Maybe for somebody else?
You're good, you're good.
You're good, you're there, Maurice. Do you all agree? Yeah.
Okay.
Because that portion comes from the aldehyde, and then this portion comes from SN2 step.
Mm-hmm.
Questions? Okay, the next couple of reactions of aldehydes, ketones we've seen before. They're not new. We are just formally just including them in the list of reactions of aldehydes and ketones, but we've seen them before. So hopefully they're extremely familiar to us. So reaction number 5, reduction of aldehydes and ketones. Aldehydes and ketones can be reduced. Does anybody remember what reagents to use to reduce an aldehyde or a ketone?
An oxidizing agent.
Well, if you're reducing, why would you use an oxidizing agent? La is
La.
one. What
La.
else?
BH3.
NABH4.
Not BH3. Sorry?
NABH4.
Sodium borohydride.
Oh.
So the two reagents used to reduce aldehydes and ketones is either sodium borohydride or La. Now, what does La stand for again?
Lithium aluminum hydride.
And
Four.
if you are using sodium borohydride, what is it used with, generally speaking? What do we use?
Methanol.
Generally, methanol, ethanol as the solvent. And what about La? Do we use the same for La?
No.
No. What do we do instead? That's a two-step process because La, being a very strong reducing agent, should be not used without anything protic, so we have to bring a protic source later on as a separate step. Does everybody remember that?
Yes.
We also wrote a mechanism, but what would be the product?
Oh.
If an aldehyde or a ketone is reduced with sodium borohydride or La, what's the outcome?
An alcohol.
An alcohol. Alcohol. What kind of alcohol does a aldehyde produce?
A primary.
Sorry, I lost track of where I was. Primary, and if it were a ketone, what kind of alcohol would it be?
Secondary.
Okay, cool. So let's do this a couple of times just to remember. And mechanism. We did write a mechanism for this tell me what is the product, what are the products here? No? Done?
Keto.
Wanna tell me what the product would be?
Oh, I just finished writing down.
Okay. Cyclopentanol for the first one, do you all agree?
Yes.
And the
Okay,
second one would be
Let's, what would it be?
phenol.
No, not phenol. You lost the carbon.
Oh, okay.
What would it be? Anybody?
A second,
What would the product be? Benzyl alcohol.
benzyl
Absolutely.
alcohol.
Benzyl alcohol is of course not an IUPAC name. That would be phenylmethanol, but let's quickly write a mechanism at least once so you remember the mechanism. Can someone tell me what's the first step?
Hydride comes.
From where?
From
Hydride from the NABH.
Which part of NABH4 gives us the hydride?
one of the H.
So not the sodium ion, that's just a counter
Yeah.
ion. It's the borohydride, which is a source of a hydride anion. Isn't that right? It's electron rich. It wants to get back to its neutral state. And the only way it can do so is by donating a hydride. Where will that hydride go?
On the oxygen? No.
Is that electron rich, electron poor?
Rich.
Is hydride electron rich?
Rich.
Then why should rich go to
Electrophilic
rich?
carbon?
So hydride acts as a nucleophile, attacks the electrophilic carbon. Right? What does that create in this case?
O minus.
Becomes
Alcohol.
Alkoxide.
alkoxide, O minus, and then what does this guy need to do?
Deprotonated.
And where is the did you say
B.
deprotonate? Deprotonate. Sorry.
Deprotonate.
I heard depro- And where is the proton going to come from? In this case, that's coming from methanol, giving us the proton to give us the product. And it's the same with La, the mechanism is the same, it's just that the hydride is coming from aluminum hydride, but the mechanism is the same. Do you guys remember this? Next reaction, also we've seen before, in fact we saw it last quarter, but we also did it this quarter as well. And it's exactly the same as this in terms of the mechanism, and that is reacting with a Grignard. Right, we've seen that aldehydes and ketones react with Grignards. Can someone tell me what is the outcome when we react with Grignard?
Attach.
With
Two are repeating.
why two?
Oh, just one, sorry.
This doesn't have a leaving group, right? Bad leaving group, bad leaving group. That's for esters and acyl halides that do have a leaving. So what will this give us? It will give us an alcohol, but with an added R, right? You're adding carbons. So we've seen this also several times this quarter as well as last quarter. So, and you should know the mechanism, you should be able to write a mechanism. Guys, please tell me, what is the product? And by the way, how many equivalents of Grignard needed for this reaction? Just one.
Just
Exactly.
one.
Because Grignard is reacting only once. So what will the product be? And let's write a mechanism. Exactly the same mechanism as the reduction reaction. The only difference is the nucleophile. Yeah. Okay, since you're there, why don't you write the mechanism too? Unless you don't want to. That's Do you all agree with the products? Yes?
Yep.
Yep.
And then, of course, the mechanism. Nucleophile attacks the electrophilic carbon of the C double bond O, creates an alkoxide because there's no leaving group. And so the alkoxide gets protonated, becomes there. Perfect. Does that sound okay, everybody? Questions?
Yeah, well, that's just normal.
Yeah, exactly.
I mean, no,
Exactly.
I don't see anything.
I like it when you start calling these mechanisms normal.
Oh,
Oh, that's so cool. Now this is normal. Great. Okay. Just trying to wait. Oh, you lost it. No, you didn't. Oh, one thing I won't do, Dash, is make an anion. There's no anion. There is. This just goes with it. So it's not that it breaks up first and you've got anion, free floating anion, which then goes attached. It's a simultaneous process. Yeah. Perfect. You can just point it to the product if you want. But yeah, absolutely. Okay, the next reaction that we are going to talk about, again, please notice the mechanisms are so similar from one reaction to the other. It's the same sequence of events over and over again. The only difference is the nucleophile changes, right? If the nucleophile is this, you get that. If the nucleophile is that, you get this, blah, blah, blah. Everything else is kind of the same. So the next reaction is reaction with a primary amine to create an imine.
Imine.
Imine is created when aldehydes and ketones react with primary amines. Does anybody remember what's a primary amine?
An amine at a terminal carbon.
So, doesn't have to be, by the way, a primary amine doesn't have to be at a terminal carbon. Does anybody remember what's a primary?
Would that be N and 2H?
Exactly. Now it can be in the middle of the chain.
Yeah,
But
NH2.
you're right, it is one that has two hydrogens of the nitrogens, that's primary amine. Secondary amine, just to remind everybody, this is for amines. That's where amines are different from alcohols. How you decide whether an alcohol is primary or secondary or tertiary is based on the carbon the alcohol is attached to. But for amines, it's based on the nitrogen.
Oh.
So yes, And secondary amine is where the nitrogen is connected to two R's, one hydrogen. Tertiary is no H's, just R's. And there is also quaternary, although that is not neutral. That will become a cation, ammonium. That's a quaternary ammonium ion. But coming back to the reaction though, aldehydes and ketones react with primary amines to create imines and water. So if you have an aldehyde or a ketone, react with primary amine in presence of an acid catalyst to create an imine and water. With that information, can you guess what an imine is? The byproduct is water. Can you guess what imine is? You're saying swap the O in the end?
Yeah, in one
With what kind of bond?
one
between
bond.
them? Well, if it's one bond, then shouldn't
Well,
somewhere
I
there
mean-
should be a charge?
Let's see, N, and then there's another R. We should add another R. No. Okay.
So think about it, guys. The byproduct is water. Where is water coming from?
H2
H2O,
and O.
right? So you're in a way you're correct. And let's just swap the nitrogen and oxygen. But what kind of bond between the nitrogen and the oxygen? Exactly. Can't be a single bond. Because then you
Oh.
will have charges
Yeah.
somewhere. That's an imine. It's also called a Schiff's base. In biochem, they don't call it imine, they call it a Schiff's base. But again, who cares? You can call an apple Timbuktu, it's still an apple, right? Schiff's base. So in case you come across that term, which you will if you do biochem, please remember. I'm laughing because who's going to remember that like 2 years from now? But if you can, it's just an amine. It's nothing more. Okay, let's look at an example. Write a mechanism. Where's my cheat sheet? Fine. Why do I need a cheat sheet? Okay. Please tell me what's the product. Yeah, for now. Then we write the stepwise mechanism. Yeah, what was the product?
Swap the O at the end and put a phenol at the end, keeping the double bond.
Last page. Agreed? Everybody? Okay, let's try and write a mechanism step by step. What do you think is the first step of this process?
The phenol goes into
The phenol.
no,
Phenol goes nowhere.
no, goes nowhere.
Second?
The oxygen from the
Exactly. If remember, when we were discussing
Oh,
the
yeah.
general sequence of events, if there's an acid, the first thing you do is protonate the
Sure.
oxygen. Protonate the oxygen. Okay, so if that gets protonated, then what? Once the oxygen
Then
gets
we-
protonated,
We have a positive.
okay, yeah, but then what? Next step. What happens in generally speaking, once the oxygen gets protonated, what's the next step that comes after that?
The double bond.
No. The
Guys, we talked about the general sequence of steps in all of these mechanisms, right? If there is an acid, if there is no acid, nucleophile attacks the electrophilic carbon and then the O gets protonated. If there is acid, oxygen gets protonated first and then what?
The nucleophile comes in.
What's the nucleophile here?
pH.
So the amine, the primary amine is the nucleophile. In this case, aniline. And Where? From where? The nitrogen. Why? Because it has a lone pair. Isn't that right? That's the same sequence of events, guys. We are not really changing any of those yet. Okay, so the nucleophile attacks the electrophile, creates a tetrahedral intermediate. Okay, what do you think should happen next? Guys, I need you to be able to recognize the patterns here. What am I missing?
There's a plus that in the end, not nitrogen.
Where?
In the end,
On the end.
In the end, where? On which atom?
on top,
On the
Which
nitrogen.
atom?
nitrogen.
Oh, I didn't hear that part.
Oh,
Absolutely.
I'm like,
Not the nitrogen. Like, where? Which? Exactly. Now what? What would you predict happen next?
well, we need to deprotonate it.
Okay, you need to deprotonate it. Okay, but not from the same. Meaning there'll be two separate steps. One step where this deprotonates, another step where that gets protonated. It's called proton exchange. It's basically can't be intramolecular. The transition state isn't big enough. For intramolecular processes, transition state of 5 or 6 is good. Anything other than that is not. So the point is, yes, you're recognizing that somehow this has to get rid of a proton and this has to get a proton, so it becomes a leaving group.
Mm-hmm.
Everybody's recognizing it?
Yeah.
Just not in the same step. It's not this taking a proton. That's it.
No.
Because it's not intramolecular. It has to be intermolecular. Now, how do you show it? Again, there are different ways. People have their own versions. One option is, let's just do it one step at a time. Let's do that first. And then show that getting protonated again. Sure, totally fine. You can do that. Or, here's another way sometimes people show it, is, so that's going, and I will just have a proton here. This is taking proton, you just go directly here. Either way, it's a matter of choice. The only thing is, you need to make sure that you're showing this as in two intermolecular processes, not an intramolecular process. Yes.
Well, Vince and I were wondering, where does the H go? It just breaks. Just where does it go? Like,
Are we just taking one proton in this entire system?
Huh?
Oh, where does the proton go? Is that what you
yes,
said?
in this, in this one here. Like when
So-
you break it and it just the red
This one?
there. Mhm.
Yeah, so did I just use H plus?
Yes.
Practically speaking, no, you gotta be practical here.
Yeah.
Do I have bottle of H plus?
No.
Do we have bottles of proton sitting?
No.
What do we actually have?
Acids.
Oh, okay, yeah, that's what that means, but what do I actually have?
Water.
You have hydronium, isn't it? Isn't H plus the same as hydronium?
Yeah.
Or maybe it's HCl, maybe it's TSOH, maybe it's whatever. The point is there always something with H plus?
Yes.
Can that something come and take the proton?
Mhm.
Do we have to actually show it? It's a choice. It's a matter of choice of how you prefer to write
Okay.
it. I wrote H plus because I had H plus there, right? So I took an H plus, so I'm giving away an H plus.
Okay.
But if it were H3O plus, then there's water. If it were HCl, there's Cl minus, so on and so forth. Does
Got
that
it.
answer your question?
Definitely. Yeah, that's what I thought,
So-
but I want information.
Exactly. So those are all those things that are happening in there when the reaction is taking place. So please, whether you show step by step or you just show this gives a proton, that takes a proton and go directly here, totally okay. Questions so far? Say that? H plus is catalyst. Yes. Yes, exactly. It should be. In this case, it is.
Did you say that we could show it in one? Of course, they're different, but in one step we could show like that.
You can either
Oh,
show
okay.
this or you can show this.
Okay.
This is giving a proton, that's taking a proton, directly comes here.
Yep. Okay.
So, what's next though? So ultimately we get to this point.
Either from
Leaving group. You got a great leaving group. Why is that? Sorry. When that leaving group leaves, what will it create?
Water.
Don't care. What about the organic stuff? Carbocation. Have we seen this kind of a carbocation before?
Yes.
Please. Yes?
Never in my life.
Yep.
No.
What's so special about this carbocation? From where?
The nitrogen.
You did it with oxygen. Well, it's the same thing. This has lone pairs too. Why can't that do it? Same thing. It is a resonance stabilized carbocation coming from the lone pairs which you've seen before, right? So what would you expect to happen next?
Or something takes the proton.
From where?
From the nitrogen.
So since I'm just doing H plus all around, I'm just going to do H plus, but yeah, you're right, something's gonna come and take that proton, recreate the catalyst, give us the shift space, the imine, and the catalyst. Again, please, instead of looking at specific mechanism, do you see the trends, the patterns? The mechanism is exactly the same as acetal mechanism, because you're protonating that first, and then the nucleophiles attacking, and then the OH is getting protonated, so it becomes a good leaving group, makes a resonance stabilized carbocation, blah, 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 same thing. Agreed? Everybody okay? Questions? Is it really catalytic in protons? Let's make sure. Used one, created. Okay, so that's balance. Used one, created. Perfect. So it's catalytic in H plus as well. Everybody okay?
Yes.
Questions? You want to write it one more time?
No.
No.
We're
you
good.
better know.
I'm good at, but I don't know. Everybody else?
Oh, Mar is saying you're good?
Yeah.
You got it? Okay, cool. Then we don't. Okay, fine. Is that okay with everybody? Or is Mar the spokesperson for everybody today? Okay, fine. Let's do a couple more examples though. You can practice writing mechanisms at home.
Well, unless there was like one that's intra or something. No, but it's the same. Never mind. Or something tricky that we could go over. Like in an exam.
You said tricky?
Yeah. Give us the trickiest one.
Trickiest? No, there's no such thing as trickiest. It can get tricky as much as you want. It's not tricky really, but can it happen intramolecularly? There is an intermolecular reaction. One molecule brings the C double bond O, the other one brings the primary amine. But can it happen within the same molecule?
Yeah.
Absolutely. As long as the new ring, what sizes are desired for a new
5
ring?
or 6.
5 or 6 then it can.
Bigger than that, or just 5 and 6?
5 or 6 is the preferred ring size because those are the most stable rings of all the cyclic structures. So while you guys are working on that.
reactions.
No, whatever. Oh, darn.
Did you do? Those reactions over there are actually some diagnostic tests we do to ascertain if there is an aldehyde or a ketone in a compound. So we don't do this anymore. We used to do a lab that ran for 4 weeks of the quarter where I would just give you, tell me what this is. Literally, here is something, tell me what it is. So you got to do some diagnostic tests to figure out what are the functional groups. Is it an alcohol or an aldehyde, ketone, blah, blah, blah. So these are some diagnostic tests that are done to ensure that there is an aldehyde or a ketone in a molecule. But it's really nothing but that. It's the same reaction. But that's the purpose those are used for.
Is this one correct?
If not, you draw yours. We'll see. Why do you think that's not correct?
Miss,
Yeah.
I have a question.
Yes.
So, in the textbook,
Yes.
the mechanism,
Yeah. They did that first. I was noticing that too, but it's an acid. So I think we should just protonate first and then go. Yeah, I was
would it
noticing.
be wrong if I
No. I- This reaction is specifically for primary amines. Something to also think about. An amine. More?
Now I remember.
What about that board? Nobody else wants to go? It's oh, Annie's coming. Yeah, please go. Yeah, great. Dash. Ali was going to do that one.
No, it's okay.
It's fair game.
Okay, no. Now she
Very
sat
okay.
back down.
It's okay.
Next time, Ali. What about the other one? No? Not yet for that one? I don't know what that is, but okay. Ooh, carbon with 5 bonds. Careful, you lost a carbon. There we go. So my kindergarten through 8th grade, this is like way back when, I went to a Catholic school. With fathers and nuns, sisters and everything, the whole shebang. And I remember our principal, middle school, whatever, one of the sisters. So, in grammar, they used to be very particular about grammar. That's why I think my grammar is way better than my kids and all. But that's something I always remember. Let's say if you were saying Carter and I were together and I said, I and Carter went blah blah blah. She would smack you and say, first. Always stuck in my head. Oh, there was plenty of smacking. Rulers. But that always stuck in my head that, oh, I always go back, go in the second place. The other person always, so it's always Carter and I, and not I and Carter. But now I see everybody mixing it, and I cringe on the inside because Sister Mercedes is constantly speaking in my head. Similarly, there was a chemistry relationship here. Carbon with 5 bonds. If I see carbon with 5 bonds, again, it's like, it's very cringy. No, please, don't do carbon. So hopefully that will stick in your head 10 years down the road. Sumita, carbon with 5 bonds. Perfect. Okay, let's look at them. Do you all agree with these two? Agree? Yes?
Yeah.
Perfect. How about, that's that's again FII. That's called hydrazine, so this is an oxime. Who cares? What is that? Hydrazine, so this is called a hydrazone. Okay. This is called 2,4-DNP, 2,4-dinitrophenylhydrazine. So the product is a 2,4-dinitrophenylhydrazone. Do you all agree with the products? I don't agree with that one. This one. Why? The reaction is for primary amines. Amines. Is this an amine? What is it?
An amide.
An amide. Yes. That is the amine.
Oh.
This is the amide. So that would not be correct. It's for primary amines. So
Here was a tricky
it
one.
would have to react from the other end because these are amides, those nitrogens. Do you guys see the difference? Okay. What about here? Do we agree with so again, this portion comes from the ketone and then this comes from the primary amine. Looks good. Again, that's the aldehyde part because there's a hydrogen here and then hydrazine. Perfect. Do we all get it?
Yes.
Everybody good? Cool. Now, amines, let's take one. How about we use this as an example? Because you've seen this also plenty of times now, so hopefully you can tell me. What's the byproduct?
Water.
Water. Again, we've seen this so many times now. This reaction is reversible. What would I need in order to make the amine go back to the aldehyde ketone and the primary amine?
Water.
In presence of, absolutely, in presence of the catalyst. You need catalyst for both sides. You need a catalyst to go this direction, you need the same catalyst to go in the other direction too, but you're absolutely right. If I had a dilute acid, I could just go back. Everybody sees that? Yes, let's do that a couple of times. Again, mechanism writing, absolutely, to make sure you understand the process. Okay, so please tell me. We already did that one. So what should I use if I'm going in the reverse direction?
Water.
Hydronium. I mean,
Water with acid or hydronium, dilute acid, whatever you want to call it. They all mean the exact same thing. Can you tell me what would be the outcome?
Ketone.
Which one?
1, 2, 3.
it's
Two pentanone.
2 pentanone, 1, 2, 3, 4, 5, very good. And, right, it breaks right here.
And the primary.
The primary amine. You don't need to be able to name that yet because we haven't done it. But do you guys agree? Please go ahead, take a stab at the mechanism. Think about what should be the first step, last step. Again, it's the exact opposite of the forward because these two are in equilibrium. The mechanisms are also in equilibrium. So,
right.
what should be the first step?
Protonate. Nitric.
Sorry, chlorinate what?
Nitrogen.
Nitrogen. Okay, then what? water attack? Do you all agree? Exact opposite sequence of events. What you saw in the forward mechanism, this is exactly the opposite. Okay, so if that attacks, what does it create?
A good living group.
No, but the leaving group will take you back.
Oh yeah, yeah.
It
That's
is a good leaving group, but then you're going in the reverse.
yeah, yeah. I keep.
Okay.
Okay, so
What next?
the OH2 gets deprotonated.
And, okay, yeah, and? So you're right that this is going to give a proton. And who's going to take that proton? Somebody. This is going to get a proton from somewhere. Isn't that right?
Yep.
Proton exchange. One is giving, the other is taking from somewhere.
Yeah.
So what does that do? Agreed? What next?
Well, deprotonate.
But
But we
deprotonation
just
will
yeah,
take
yeah.
you
No,
back.
no, it'll take us back.
Think forward. We need to go in this direction.
Mm.
There's a leaving group. Exactly. That's a great leaving group exactly for the same reason
Oh,
why
that's where it
H2O
breaks.
is a great leaving group. Because you're going to create a neutral, a weak base.
Mm-hmm.
That's a good leaving group. Okay, so what does that create? A carbocation. A carbocation that is resonated, resonance stabilized. Exactly, and the amine, and the primary amine got kicked out, and so we have that now. And the resonance stabilized carbocation. What does that guy need to do? Anyone? What does this need to do? Doesn't it just need to deprotonate
Yes.
and become the ketone? So.
And you could do either one, right? Or not? Either resonance you could do. Or...
Oh yes, yes, you can do it with either resonance. That's totally fine. The point is, two things I want to point out. A, the mechanism for this direction is exactly the opposite for the opposite direction, the sequence of events. B, it's the same mechanism as acetal. It's exactly the same thing over and over and over again. The only thing that changes is the nucleophile, so suddenly we have a different outcome. Do you all see that? Everybody. Okay. Please tell me what would be the product, the mechanism you can practice at home. Product. Anybody?
Oh, it breaks, right? I can try.
It's not okay for you to just sit there and nod at each other. Go do it over there. Let me see. Yeah. Okay. Is that what that? Yeah.
I'm
You what?
I'm sort of stuck.
You're stuck?
Yeah.
What? Okay.
Do you all agree?
Yes.
Basically, it's that carbon-nitrogen double bond that is breaking where you're adding water. Can we draw it differently also? 1, 2, 3, 4, 5, which is nothing but 1, 2, 3, so.
1, 2, 3.
Same thing, you're just looking at it differently. Agreed?
Mhm.
Everybody?
Essentially, what I'm getting is that you're cleaving that C double bond N, and on the N side, it's an amine.
Isn't that what we did?
On
when
the other
you're
side
hybridizing?
is a ketone. Yeah.
You're adding water across the C double bond N and then breaking that and creating the hydrolyzed product. Exactly.
Mhm.
So please do practice writing these mechanisms. Of course, they're all the same over and over again, but do write. But let's go to the next reaction, which is similar, but a little bit different. This is called enamine formation. Guys, do you remember enol?
Yes.
What is enol?
A alcohol of a C double bond a C double bond C
What does this imply?
alkene.
C double bond C alkene.
Yep.
And what does that imply?
Alcohol.
So an enol is when you have C double bond C and OH attached to it, right?
Right.
And we learned how they are very unstable. Typically speaking, they tautomerize to the keto form, ketoneuralgia. We've done that. So anyways, the point though is, any guesses what an enamine is?
C double bond C
And-
with an amine on it.
Exactly.
Yeah.
That's pretty much what it is. So an enamine is C double bond C ene with an amine on it, and whatever that is. That's an enamine. So aldehydes or ketones, ooh, I have to draw this a little bit differently because it's tiny, it's a bit different. Aldehydes or ketones that have at least one alpha hydrogen. This is, excuse me, yes. So as long as there is one hydrogen on the alpha position to the C double bond O, next to the C double bond O, reacts with secondary amines, not primary, but secondary amines. In presence of an acid catalyst. Also loses water. It is a dehydration reaction, but intramolecular, not intra. But the point is, what's the product? So the water goes from here. Of course, this H, of course, this O.
And one of the H's on the alpha carbon.
Exactly. The water comes out H2O. From the alpha carbon loses one of the hydrogens as proton in the mechanism, which we'll write. But what's the product? Guesses?
The bond between C and the H being removed will become a double bond.
Okay, so this becomes a double bond? Okay, so
And then the carbon will be single bonded to the nitrogen.
exactly, and whatever is on the nitrogen already. That's an enamine. Enamines are very common in organic syntheses for certain reasons, which we haven't
And
learned
amines
yet.
are stable,
Yeah,
compared to
absolutely.
enols.
Absolutely, unless you do something with them, yeah, absolutely. There's not, I mean, oh, you mean compared to enols?
Mhm.
Oh, yes, absolutely. Okay, so let's look at a couple of examples and write at least a mechanism at least once, and then we go to the next one. So let's say we have cyclohexanone reacting with diethylamine, which is a secondary amine. What would the product be?
Is it always just gonna be with a second?
This one is for secondary, yes.
sp2 carbon. You're saying
Are we writing everything?
Okay, don't talk, just do. Go ahead. What were you saying, sp2 carbon what?
yeah, say because to make a double bond, so you can sp2.
Oh, I see.
Then no single bond to negative.
Yeah, okay, you mean the alpha carbon becomes sp2, yes. So you were asking, about the secondary, right?
Yeah,
This has to be secondary.
always has to
Yes,
be.
for this one, primary creates imines, which we saw earlier.
Oh, yeah.
Secondary creates enamines.
Yeah.
Tertiary can't do anything because they don't have a hydrogen on them. Do you all agree?
Mm-hmm.
Yes? Let's write a mechanism. Please, you will tell me. You shall tell me. What will be the first step?
Well, protonate.
Where?
Yeah, the O.
Okay.
Oxygen.
Next.
The nitrogen is gonna attack the carbon.
The NET2.
ET2, right? Two,
Yeah, ET2NH.
Attacks where?
The carbonyl.
Because that's a nucleophile, attacks the electrophile. Agreed?
Yes.
Okay. What next?
Well, what do we get? Let's see.
Do the whole thing where you take one proton and then move it up.
Proton exchange?
Yeah.
This loses a proton,
Yeah.
that takes a proton. Okay. Then what?
Kick out the water.
Create a carbon.
Excuse me. Kick out the water,
Mhm.
create the more resonance stabilized carbon cation.
Cation.
Agreed?
Resonance stabilized.
Okay, next what?
Um,
This is where the difference is.
remove one of the alpha hydrogens.
Because there's no hydrogen left here for anything to happen here, unlike primary amines. So therefore, the choice is one of the alpha hydrogens.
Oh.
That's why, because there is no hydrogen here
Oh.
anymore. Till now, everything's exactly the same. Okay, remove, the alpha position loses a proton and,
Creates a double.
creates a
The double bond.
double bond.
There. Oh.
Exactly. Creates a double bond, giving us the
Interesting.
enamine instead of. Everything else is exactly the same. Same steps. Do you all see that? Everybody okay? Make sense? Okay, no mechanisms again, you can practice at home. Just give me the other stuff, so.
Sunita,
Yeah.
for that second one, you're not saying that the first one is going. Is
Oh,
creating a-
shoot. Yeah, okay. Yeah, thank you. No, I wasn't.
Okay, I'm just making sure. Getting confused.
Yeah. Thank you. we have 2 recordings going on today.
I just want to make sure for Jane that.
Ah,
The video is super helpful, thank you, Mark.
Oh, good. I'm glad.
Is it just anything?
It's just in case one
what do you
fails.
think? In the language of Ochem, what does that mean? Oh, why are you looking at her?
Oh, is it just?
What does this mean?
Oh. Oh.
Same thing, right? So do you guys actually watch the videos?
I do. That's the only way I can.
Just you? Just you?
I
watch
no,
it?
but not everybody.
So do you guys like
Sometimes.
speed it up and speed it fast forward till because there's so much empty space.
I go back like 20 times to this
Oh my
till I
goodness.
understand.
That's a lot.
Transcripts you can search up too.
Oh, that's true. Yeah, yeah. If you know what you're looking for, you can just search up on it.
But yeah, then you can skip the
Yeah, exactly.
or pause it or. Well, that's what. No, we didn't have videos with you. We had them with Mark.
What? Yeah.
Videos, not with you. No, you never did videos
For what?
for classes in camp.
140 I do, but I don't know how many people watch.
Oh yeah, you
I
did.
mean, out of 75, 15 come to class. I'm like, what? And then maybe 5
No,
will
no, I
watch a
remember.
video.
I did. Yeah.
Yeah, I don't think a lot of people do.
Oh, because we had to be in lecture in order for you to send us the video, right?
No, the videos are there.
Oh, really?
I didn't have any. I don't require attendance. You want to come, come. Don't want to come, okay. Have a great day.
Oh, okay.
Because,
I'm not remembering any.
but, so here's the thing. Sorry, what?
It's fine. Yeah, I think it was. I think it's alright.
The age. Where do you?
Maybe.
Is it,
Is there some?
shouldn't the age? Oh wait.
Does it matter
Wait, does it
which
matter?
alpha hydrogen you
Near
Why
the.
not draw the other one and then we can answer, does it matter which alpha hydrogen it
It
goes?
should be the
Can we draw the other one?
by the end.
Because there are 2 different alphas, right?
Yes.
So what would the other one look like?
No.
Okay, yeah.
Oh, it is?
Yeah, now, what? Yes, why? Why not?
I'm confused. I'm
No,
confused.
no, you're
myself.
good. You're
I'm
good.
confused myself.
There's an alpha here which is giving us this product.
I was.
There's also hydrogen here, right? And that's also alpha, so good. So the question, does it matter? Is one better than the other? What do you guys think?
No.
Oh no, look carefully. Please think before just
What's the
choose.
sodium alkene?
Exactly. Isn't one alkene more stable than the other?
Yeah.
So should there be a major product and a minor product?
Yes.
Yes. Yes. So does it matter which alpha proton goes?
Yeah.
Yes. The one that creates the more stable double bond. Absolutely. Totally agree.
would there also be a third product?
Oh really? Where?
What if you went to the opposite side of the
It's the alpha of this guy. Those are the only 2 things. What do you mean opposite of where? Dash, come on, what do you think?
I was thinking in nitrogen.
But it's the alpha of the C double bond O, period.
Mhm.
Alpha hydrogen from C double bond O only.
Oh, wait.
Do you all agree?
Mm-hmm.
Okay, cool. Again, please do practice writing mechanisms. By the way, let's go back to that equation right there. This is the forward direction. So what can you say about reverse? Do you think that's possible?
Mm-hmm.
If so, what will you use?
H2O,
Just H2O?
dilute acid.
Because you do need that catalyst still, right? You do need H plus
Yes.
as a catalyst, and then water is the reactant. So it's exactly the same way, just like amines can be hydrolyzed, similarly enamines can also be hydrolyzed back into the parent aldehyde or a ketone. So please go ahead, tell me.
Benzophenol. Are we reversing?
Yeah, we are reversing it, yeah.
Yep, we're reversing it. Turning the enamine back to ketone.
We're doing that reaction here.
No, don't sit like that.
Okay.
No, I've lost the count completely.
Mhm. Where is your carbanion carbon? Where's your alpha? Yeah, exactly. And then what's the amine?
Oh,
I'll show it.
how do I draw that?
No, it's a product, so don't show in the arrow. That's a
Oh.
product,
Oh,
right?
yeah,
So
yeah, yeah.
plus that, because the reaction is this way. Exactly. So once again, where are the bonds that are breaking? Where is water going? Parts of water going. Bonds breaking right here. That's the bond that was formed,
Oh.
right?
Yep.
One H is going here, one H is going here, O is going here. Isn't that right?
Mm-hmm.
Everybody gives us those products.
Oh, I
Just
was.
the opposite. This is not imine, this is enamine, which means that's your alpha carbon. So if you're doing the same here, get creative. What is the product? Anybody?
One, two, three.
not quite.
No, am I off?
Yeah.
No.
Because if your connections, your bond connections are off. Anybody else? This is a tricky one. This is definitely a tricky one. Remember, we are adding water.
Our byproduct would be NHCH free.
Yeah.
What did you say?
I just can't see it.
Oh,
She just said it was wrong. Maybe you think I'm right.
okay, you got till there, but do you think that's done? What do you have left after this point? A good first step. What is that now? You write that is aldehyde on this side. This part is aldehyde.
Okay.
What about that side? What is that? It's an enamine. Enamine. Can't it also hydrolyze?
Oh.
What?
So this one is a tricky one. It's a creative way of doing this reaction, which is not
So-
exactly like what you
Do you
see.
cut it again?
The idea is the
I was
same.
just saying, is the nitrogen attached? Or is
To what?
something separate? Like, will I get separate product from the nitrogen?
You tell me.
Oh, no.
Is it an enamine? Is
Yeah.
it an enamine?
Help me out.
You're adding 2 instances of water.
Yes. Why not? We don't count water molecules, we just dump, right?
Yeah.
It goes wherever it needs to go and does whatever it needs to do. We don't have the choice. I do feel you have too many carbons though, or maybe not. Yeah, I think you have one. Oh, no, you don't. I'm so sorry. I'm miscounting.
Yeah.
Yeah. And then what happens to the nitrogen? Oh,
I thought I had type 2.
No, it's B.
there you go. But you write so big that you take up all of my board space.
Yeah.
The 4
space.
boards.
I don't know, can you guys read what this says? Are you able to read this? Oh, really? Oh God, you guys have really good eyesight.
I have good
You
glasses.
can?
I have good glasses.
But you're absolutely right. There are 2 enamines here. This is an enamine. Do you see that? Enamine.
Mm-hmm.
Read? But this is also an enamine.
Mm-hmm.
Enamine. So this can hydrolyze twice.
Mm.
In both cases, hydrogens will go. Where will the hydrogens go? Hydrogen, hydrogen, oxygen the first time, right? But then hydrogen, hydrogen, oxygen. So you're breaking this, end up with a dialdehyde and a amine right there. Absolutely. Do you guys see that? Yes? Cool. Okay, that's enamine formation. Let's go to the next reaction, that's cyanohydrin formation. Again, everything is exactly the same pattern, mechanisms, blah, blah, blah. So, what is a cyanohydrin? It's a fancy name for something you get
Cyan.
when an aldehyde or a ketone is reacted with HCl, hydrocyanic acid. Same thing. Now, you've written this mechanism like so many times, you can probably tell me where will the CN go? Oh, come on, guys.
Place the R.
That's not okay. It's an acid.
Mm-hmm.
So where will the CN go?
In place of the oxygen.
In place of the oxygen?
Well, it will attack the
to the
carbon.
carbon.
Mm-hmm.
Where will the proton go?
Oxygen.
So what's the product?
Alcohol.
Not an alcohol. cyanohydrin. So we are basically adding HCN across the pi bond, just like we added water, just like we added alcohol, just like we added amines and blah blah blah. Now this time we are adding HCN across the pi bond, and here is your HCN. This is called a cyanohydrin. Now, just FYI guys, HCN is again not something we keep. HCN is generally created in situ. When you're doing a reaction, you're really creating it as it's doing its stuff. So we don't actually use that. We use a combination of potassium cyanide with an acid. Potassium cyanide with acid creates HCN and then the reaction. So, do we have to write a mechanism? Because we've written it 1,000 times, I feel like already. What's going to be the first step, anybody?
Oxygen gets protonated.
And then? Got it. Okay, so then please make sure you know how to do it. Let's do some examples. Now, by the way, what's the purpose of this? The nitrile group, the cyano group, whatever you want to call it, is actually a very useful group synthetically speaking. The CN group or the nitrile group, this guy right here. So we can either hydrolyze the nitrile, so this carbon right here, and we look at the detailed mechanism of that step next chapter, I think, but this becomes a carboxylic acid. And of course ammonium and all, but who cares? So it's this carbon is that one right here. We can also reduce the nitrile using La, only La. Sodium borohydride doesn't work for it, it's La, in which case the CN group becomes a primary amine. So that becomes primary amine. So that's really useful in terms of synthesis to be able to, get to other functional groups from there. Okay, so let's try this. Fast, please. Might have to heat a little bit.